What's up, everybody? Today we're going to be looking at section 1.4, polynomials. And so, what is a polynomial? Well, polynomials, poly, the word poly in polynomials means many, and nomials means terms, so many terms. So, definition of a polynomial is a linear combination of variables raised to a non-negative integer power with some coefficient. Okay, if that just sounds like hogwash to you, that's totally fine. So here's an example of a polynomial. It has an integer power, right? 3. It's non-negative, so it can't be negative 3. It has to be positive 3. Basically, a non-negative integer power means just a whole number 0 or greater. 0, 1, 2, 3, 4, 5, okay? With some coefficient, which means it can have a number in front of it, right? In this case, it's 2. Cool. Here's another example of a polynomial. Remember that poly means many, so here the 3 is kind of like signifying the many. These are the coefficients. In this case, it's 2. The power of the x is 2. That's, greater than 0 and a whole number. The coefficient of the second term is 3. The power of the x is 1, which is fine. And then we have the 7. And so you may be asking yourself, well, what's the power of the x here? I don't see one. Well, there's technically always one. It's just x to the 0, right? And anything to the 0th power is just 1, right? So a number by itself, which we call a constant, is a polynomial as well, because you think of it as x to the 0th power. So what's the rigorous definition of a polynomial? It's basically this. It's just a whole bunch of, all the a-n's here are just numbers, okay? And the x to the n's are just, like whatever power it ends up being. So, because it could go on forever. And so it could be x to the 7th, right? It could be x to the 70th. It could be x to the 700th. It doesn't matter, right? We're just going to list them in order, though. So if we had a whole bunch of stuff, and then we had an x to the 5th, right? And then x to the 3rd. And, all of these can have numbers in front of it. So that's kind of what this general definition is telling you. It's just a whole bunch of terms with numbers in front of it, and x's to some power. And so in a sense, you can kind of think that all of these are always there, but if you don't see one, so for instance, you're like, okay, well, I have 2x squared plus 3x plus 7. Well, if you're saying they're all here, where is the x to the 3rd? Well, it's there. Okay, it's just the number in front of it just happens to be 0. So basically, it essentially just deletes that term, so you don't really see it, right? Just kind of like how in this case, multiplicatively, there's an x here. It's just x to the 0, so it kind of like hides itself. Same thing here. Okay, so here's a question. Is 5 a polynomial? And the answer is yes, right? The same reason that the 7 is included in this polynomial. You can think of 5 as 5 times x to the 0. And so if we go back to our definition up here, it says variables raised to a non-negative. So 0 is not negative, right? So that's totally fine. Integer, okay, 0 is an integer with some coefficient. And the coefficient just happens to be 5 here, right? So 5 is a polynomial. Okay? Okay, so here's a few definitions. So let me bring this polynomial back over here. So we have something called a leading coefficient. A leading term. And the degree of the polynomial. Okay, so the leading coefficient is the number that's in front of the biggest power of x. So in this case, it would be 2. The leading term is just the number and the x together, the largest power of x and the number with it. So the leading coefficient is just the 2. The leading term is 2x squared. And the degree of the polynomial is the largest power of x. So the degree of this polynomial would be this 2. Okay, it's not the same to that for the leading coefficient, and I guess to make that clear, I can make this a 4, and so the leading coefficient here is 4. And so what's the leading term? 4x squared. Okay? And so generally when we write polynomials, we write them in descending powers. So we start from the biggest power and we write all the way to the smallest power. So we would typically do something like this, okay, rather than something like this. Now, you may see problems where the polynomial is given to you like this and they ask you what's the leading term. It's not this one, right? We have to rewrite it so that it's in order of the powers before we can more accurately assess what the leading term is, what the leading coefficient is, and what the degree of the polynomial is. So it's not just the order it's given to us, and we need to rewrite it in descending powers of x. Okay, so how do we add and subtract polynomials? Well, you've kind of been doing this for a while, and it's basically just combining like terms. So let's say you have this polynomial, and they tell you to add this polynomial. Well, what do? We look for all the terms that are x squared. So I see an x squared term here, and I see one here. So these two are like terms, right? And then I look for, I have a x to the first power, so in the other one I'm going to look for x to the first term. So these are like terms, so I can add these together, right? And then these are just numbers, so I can add the numbers together. Just to be clear, 6x squared plus 7x does not equal 13x anything, right? These two things are not like terms, so we can't add them together. Okay? So here, 3x squared plus 6x squared, that's going to give us 9x squared. So I'm combining these two terms here. The 4x and the 2x is going to give us 6x, and the 7 and the 8 is going to give us 15. And so that is how we add and subtract polynomials. Okay? And so we will just do multiplying polynomials, and then we'll cut the video there to keep it short. So multiplying polynomials. So if we just have what we call monomials, which means just one term, 4 times 3x for instance, how do we multiply this? Well, essentially what you do is you multiply the numbers with the numbers and the variables with the variables. So you would get 4 times 3, which is 12, and then you have x squared times x squared times x. And remember, the x without a number above it, there's always a 1 here. And so we can use our product rule of exponents. X to the a times x to the b is equal to x to the a plus b. And so we get x 2 plus 1. So 2 plus 1, and 2 plus 1 is 3. Right, so this is the x squared times x gives us x cubed, so our solution is 12x cubed. Okay, so, but what if we have binomials or anything more than that? So for instance, let's say we have this polynomial times this polynomial. Well, we do the same thing that we did with numbers. So we use the FOIL method, or what I like to call it by its mathematical name, distribution. Essentially, all you have to do is make sure every term in the first set touches every term in the second set. So you can call this the rainbow method. You want to make sure the first term touches the first term of that one, the first term touches the second term of that one, and then the second term touches the first term, and the second term touches the second term, right? So now all of these combinations have been met. And so kind of like, let's use regular numbers to see why this works. If we had 2 plus 3, right, times 2, let's use a different number, 4 plus 5. Okay, if we used order of operations, this would tell us to add the 2 and the 3 first, right? So we end up getting 5. And then order of operations here, do inside the parentheses first, we get 9. 5 times 9 is 45. Cool. But what if we didn't use that? What if we use distribution instead? Well, we would get 2 times 4 2 times 5, 3 times 4, 3 times 5. So what's 2 times 4? That's 8. 2 times 5, that's 10. 3 times 4, 12. 3 times 5, 15. And so if we add all these numbers together, 8 and 12 make 20. 10 and 15 make 25. And 20 and 25 make 45. Right? And that's exactly what we got when we did the order of operations. And we'll just write that really quickly again. If we did the order of operations, 2 plus 3 is 5. 4 plus 5 is 9. Multiply these together, you get 45. And you see that these answers match each other. So it tells us that this is totally kosher to do. And so why don't we just, combine these things and make it easier and follow order of operations? Well, because these are unlike terms, right? They're not like terms. We can't necessarily do that. So the only thing we can do is use the distribution method. All right, so let's go ahead and go through with that. So we have 4x squared times 2x. The 4 times the 2 makes an 8. X squared times x to the first is x to the third. 4x squared times 3 is just 4 times 3, which is 12. X squared. 7 times 2x. The 7 times 2 makes a 14. And then the x just comes along for the ride. And then 7 times 3 is 21. And so what we would do here is, do we have any like terms in our new representation, our new expression? And we don't, right? We have 1x cubed, 1x squared, 1x to the first, and just a number. And so since we can't combine anything, this is kind of our final answer here. Right? If we did have some that were the same, then we would need to combine them, just like we did here with the regular numbers. All right, I'll stop the video there.